Okay, so look, heat exchangers. All you chemies, the one who's dean now, he told me, you know what, in your heat transfer class, as long as you teach them heat exchangers, I don't care about anything else. So I'm making the dean happy. I think if you, based on everything you learned so far, heat exchangers now is kind of a non-issue. It's a much smaller thing. So what I want to do for the few minutes we have today, tell you a little bit about configurations of heat exchangers, and then starting tomorrow to discuss some of the equations that go together with the heat exchangers. So many different configurations, for sure, enormously different sizes. So the construction. For the construction of heat exchangers, you can have these 3 types. One is the concentric tube. The concentric tube, remember when we talked about internal flow, one of the correlations was for heat exchange between 2 cylinders, an inner cylinder and an outer cylinder. You might remember the figure, right? And they have all kind of correlations for that. Well, that's one type of heat exchanger. That is the one that is in that photo there, right? You have a flow going through a tube inside and another flow that goes through another tube outside. Now, you want the heat exchange to be between the 2 fluids. So overall, a heat exchanger typically is adiabatic to the environment, right? You want the energy go from one fluid to the other, not just to the air. Shell and tube. Shell and tube are very, very common types of heat exchangers, and these are the ones you see most often here in this province, right? In this one, you have a shell that contains a fluid, and inside that shell also there are lots of tubes that contain another fluid. And as you move the fluid in the tubes, right, the inside fluid, the exchanges heat with the other one that is in the shell. To help enhance this heat exchange, you have baffles in your heat exchanger. So here you have the shell, right? And here you have the tubes, right? You have baffles such that in one, let's say, one is a hot and one is a cold fluid. Let's say this is the hot fluid. And what the baffles do is to redirect this flow to go like this. And in this case, all right, the convection coefficient would be that of a flow going across a bank of tubes, for which you also have correlations in the book. So for heat exchangers, you can go down to bedrock and calculate them from scratch. When you have a shell and tube type of heat exchanger, there are different configurations. You can have, this is called one shell and 2 passes, right? It goes and bends around the flow in the tube. What do you think you'd make a heat exchanger in which you have these 2 passes as opposed to a heat exchanger in which you have just one pass like that? The number of tubes, let's say, is the same, right? So why would you make it go and come back instead of just go? This has one tube that goes back and forth, and this has 2 tubes that go forth. So it's more or less the same area. Actually, the way you calculate these heat exchangers is as if these 2 things have the same area. I'll tell you more. I'm going to show you that this one ends up being more efficient than this, and people still make these. Why? But this is an interesting thing. By the way, the book that says nothing, but I learned this from Bill Pick, that is the professor who used to teach design. He's awesome. This is a story. Some fluid is hot, some fluid is cold, right? So you're going to have different thermal expansion between the shell and the tubes. In this case, you're constrained by the end plates. In this case, you can expand everything you want, no problem, because the tubes could expand here or could shrink, whatever they want. They're not attached to the shell on the other end, right? So this type of thing is much better from the point of thermal stresses than this other one. Isn't that interesting? I think it's awesome, right? And what you also get to see in these shell and tubes, that sometimes you can combine the shell and tubes. Now you're going to see that it's not the same having the fluid going in one way than in the opposite way. And the one thing that you don't know yet, right, about heat exchangers, everything else, even if you don't realize, you know it. But the one thing about heat exchangers is how we have exchange of fluid as we go back and forth. Look, here you have the one with the bent tubes. Right? Isn't that interesting? And then we have the compact heat exchangers. This is one in which is exchanging heat against, this one is full of fins, right? So this one is losing heat to the environment. Much like, for example, the radiator in a car. You have one process fluid is the water inside the radiator, and the other process fluid, the other fluid is the air that comes and cools it down, right? This is one type of compact heat exchanger. And the other type, and this is I'm going to show you 2 more slides, and then we're done. This one, probably you're not so familiar with this type of heat exchangers, right? So these type of heat exchangers are extremely efficient, and they are. Imagine you had a book, right? Now imagine if in the book, one page is hot and one page is cold. One is hot, one is cold. It would pretty quickly exchange heat, right? Because you have the whole area of the page to exchange heat with the other two. And that's exactly what they do. Of course, it's not a book, but it's almost like a book. So they have these plates that separate layers of fluid. And each of these layers of fluid is like a page of the book, but you have a hot and a cold, a hot and a cold, a hot and a cold, right? Extremely efficient. You can make them very compact, right? And they have very, very interesting, quirky design. So in that drawing, right, that you have in your notes, you get to see how it is designed for the fluid to go hot or cold in alternate plates, in alternate spaces, right? And you see it has like kind of a textured surface. What they claim is that that surface would give you turbulence, and turbulence would enhance the heat exchange. I'm not too sure that's true, by the way, but that's the official line. All right, so let's stop here, and we'll start talking, getting serious about heat exchangers on Wednesday. Let's get started, and I wanted to show you something. What you see that when we talked about the types of heat exchangers, so there is that's a shell and tube, right? And those can be enormous. We use those, the enormous ones in the province. You go to Syncrude or something like that, you're gonna see them. They're as long as this classroom, and for nuclear power stations, they take years to build a single heat exchanger, right? Enormous amounts of welding. Now, that said, they can be mini too. Here is a shell and tube exchanger. That is, this is actually an actual one. So don't put your fingers in wrong places because you're gonna come all dirty. So this is a shell and tube heat exchanger which I'll pass around, and you're gonna see how this part here, this is the shell, and when you look inside, you're gonna see the tubes, right? And this way you also get to see how the fluid comes one way and the other way, right? In this case, I think it doesn't have baffles. Comes one way, and the other fluid, that the tube fluid, goes from here and comes out of here. In this case, is one shell, one pass. Remember, we said sometimes it's one shell, two passes, right? And that's to deal with thermal stresses. But when things are this small, thermal stresses, you can handle them. So I'm going to pass this around. Just check it out. And then we also talked about these compact heat exchangers. And these compact heat exchangers, they had, like I mentioned, it's like a book in which you alternate the pages between hot and cold, and the page, instead of being paper, are layers of fluid. So I have another example to show you, and let's see if I can show you something here. Awesome. Look, I'm going to show you one of these plate and compact heat exchangers. Look, it's just like this one. This one in blue, I don't know why. This other one is just as blue. It's coming. There you go. Right? Now, this is a tiny heat exchanger, which I believe is a functional one. But because this is a loaner, I don't know exactly where it came from. I need to get my own. So you see here, these are what would be like the plates that separate the fluids. This and here you see these 4 holes there. They are the inlet and outlet, right? And now it's quite complex. If you look, this is one of the plates that divide the flow. You see this texture it has, right? They claim that it's to make the fluid turbulent. But if you do your calculations, it tells you that it's going to be super laminar. So I still don't know exactly what to make out about that. I asked the specialist. They say, oh, of course it's turbulent. And I say, have you checked the Reynolds number? No. Well, I did. And the interesting thing about these plates is you see that they have these black, okay, fine. Ooh. This black liner there is a seal. It's similar to an O-ring, right? But this is not an O-ring. And the way it works is that the fluids come through these holes, and some of them, you see, this is open here, right there. You see that it doesn't have a seal, and the fluid will come from there, go all over here, and come out there, right? So this is one. Now, the fluid that was coming on this hole here, this fluid is sealed, same as this other fluid is sealed. But if I flip it, look at this. Well, you don't see it clearly. But if you flip it, now this one is flowing on the other side, right? So it has this system of seals that are like odd and even, such that the fluid comes and goes hot on one side of the plate, cold on the other side of the plate. Right? It's super interesting. So I'll pass it around so you guys see it. Oh, Ying put it together and did an awesome job, but just in case, don't put it to test. And we counted the number of plates. Every year we have fewer and fewer, but by now we're getting smarter. So the interesting thing, these two things we're passing around look like 2 different animals, like a mouse and a whale. But in the end, right? They're the same thing, like a mouse and a whale and mammals, and you can infer so many things about such different animals. These 2 things that look so different, in reality, they are kind of the same. We will be using the same equations from the point of view of heat exchanger for them, right? Okay, so as you pass it around and you check it out, I want to tell you a couple more introductory things about heat exchangers, then get to the meat. And if all goes right, I want to run an example beginning to end with you. And next class, we'll wrap up heat exchangers by looking at particular conditions. This is where we stopped last class. And now, as you see, what we are circulating, you see the red indicates the hot fluid, the blue, the cold fluid, right? It goes depending on the system of seals. You get to see in the plate we're circulating how these seals are playing a role. You see, here is not sealed, right? You have the red, it goes here, and this other one is sealed, so the red just gets through. By now, I taught this class so many times that this looks natural to me, looks obvious. I know that this is not obvious. It wasn't obvious to me the first time I saw it, but I forgot by now. Please, the book has an example on this, which I have marked in the syllabus. Do it. Ask us questions. Do this before the final. Do it when we still have office hours, right? The example I'm going to do is going to be in a concentric heat exchanger, just because it brings interesting things to discuss now. But these other ones, we did ask about this in many finals before. Check them out. Right? Check them out and make sure you have an intuitive grasp about how these compact heat exchangers work. All right, so when we said, let's talk about classification of heat exchangers, we said, well, can be concentric, can be shell and tube, can be compact heat exchangers. We also mentioned that some of the heat exchangers can have fins, right? Like a radiator of a car I mentioned, or parallel plate, like the ones I'm circulating here. Now, there is another very important classification of heat exchangers that is according to its flow, to their flow, and is parallel flow, like you see there, right? The hot and the cold are flowing in parallel, right? That's one type of heat exchanger, or can be here, or can be counterflow. Right? It can be counterflow in which the hot and the cold go opposite directions, right? And of course, you have very complex heat exchangers that are a combination. For example, in one that is one shell, two passes, you have one direction of the tube is parallel flow and the other is counterflow, right? And that makes the calculations a little bit more complex. And it's your good fortune that all that complexity was taken care of by some previous grad students. I'll just give you a formula. But for now, let's just be aware that you can go the two flows in the same direction or the opposite direction in simple heat exchangers. Another thing, and you need to know this because the formulas are different, is how you call, what type of mixing you have in the fluid. So, this is a bank of tubes, and the fluid comes across these tubes, and as it goes across the tubes, for example, if we have cold air going through a bank of hot tubes, the air is heating up as it goes through, right? So in the ideal case, which is never true, but when you idealize, the air that is coming through can be mixed in this direction. So you assume that the temperature of the temperature of the air depends on how far it's going down the bank of tubes, but not across the width of the bank of tubes. Okay, that's one, and there will be a formula associated with that. For example, between the baffles of a heat exchanger, right? Between the baffles. The flow is mixed, the outside flow. The internal flow is always unmixed, right? This flow that comes through the tube, you don't mix the hot and cold in the inside of the tube. But in the outside, left and right can be mixed. Now, what is unmixed? All right, there you go. Here you have this, if you were to have these baffles or these fins, right? And they would prevent the flow to move left and right. So if you were to do the calculation, which you're not going to do that calculation, you're going to use the results of those calculations, you have to say, oh, okay, this flow as it goes here gets hotter, but this other flow also gets hotter, but in a different way, right? Much more complex problem, and you don't care. There's a formula, but you have to know if you have to use mixed or unmixed. Right? And you have to understand that in this case, left and right have different temperatures, but in this other case, left and right have the same temperature in the idealization, and the formulas are for idealizations. All right? So these are types of flows. Here we have the baffles, right? And here, as the flow goes here, you see the flow would be this mixed between left and right as it goes around this bank of tubes. And here, left and right mixed as it goes through this other bank of tubes. Right? We're not going to go into that fine detail. We could if we wanted. You have all the tools to do it. But at this stage, all I care is that you recognize the main types of heat exchangers, and you can apply the right formulas and then get the right solutions for those. So here you have more baffles. All right, this is a funny thing, because we're talking about it. We're so close to the oil and gas industry. We we keep talking about things you would use in the petrochemical industry here in Alberta, but a heat exchanger is way more than just shell and tube and those things. This is from the Olympics last year, and I thought it was so cool. They have this thing that looks like a whistle, right? What this does is keeps the warmth of your body to heat up the air you breathe. So for athletes, when they are doing this, they are breathing warm air, although they are very, very cold, right? And Olympic athletes use this. It's super interesting. And this is a heat exchanger. Now, this is a very complex heat exchanger because it's a reciprocating heat exchanger. It's not one in which the flow goes constantly. You have all the tools to analyze a heat exchanger like this. We're not going to be doing that here. Again, we can, but I think we have enough on our plate as it is, right? But just, I wanted to bring this so you guys have in mind that the world is not all shell and tube, right? Alberta is, but the world isn't. And some things are super cool because, I mean, with a little bit of knowledge, you can invent things that can be quite exciting. I want to give you a few definitions. These definitions are part of the words we're going to be using with heat exchangers, right? Now, these type of definitions are things that you're very likely to be using when you have a job, right? An energy balance, I think, is super essential, but you seldom will be discussing energy balance with other coworkers. Heat exchangers, you will. And the first definition is duty. Duty is the amount of heat that is exchanged from the hot fluid to the cold fluid. Therefore, it's always positive, right? So the duty is like when somebody asks you how many horsepower in your car, right? You know, if they tell you a puny number, it's probably a small Italian car. If they give you a big number, probably it's like a big sports car, right? And the same with the duty. Like a few watts or kilowatts means tiny heat exchanger. Megawatts, huge heat exchanger, right? A power station style. We will be learning to calculate duty. And by the way, it's trivial. Then there are these other two definitions that are commonly used, and I'm speaking mainly to the chemies here. One is process fluid. So if you care about a fluid, that's your the process fluid, right? If you are making some kind of processing oil or something like that, and you're making the oil change temperatures, that's your process fluid. Now, then you have the service fluid. For example, if what you care is about the oil, because the oil is your product, and you cool it down with water, the water is the service fluid. You're not going to sell the water. You don't care about the water, right? But you need it, right? That's your service fluid. Now, these definitions, when you talk with people, they'll be constantly talking about the process fluid. This is chemi lingo. Now, these definitions get tricky because sometimes you daisy chain your heat exchangers. So what is the process fluid and service fluid can be, what is service fluid for one heat exchanger might be the process fluid for the next. I don't know what you call that, but I'm sure when you go to industry, somebody will have a very specific name for that. Also, sometimes neither of them is a fluid you care especially more than the other. Either you care about both or neither, right? So it's hard to define process. But here in Alberta, typically process fluid is whatever it came from the oil sands.